Assalamu alaikum. I hope all of you will be quite fine. Uh, for today's lab session, I will be giving the instructions for article 2.6.5 torsional systems with viscous damping. Demonstration as the mechanical vibrations lab for session 2022. Previously, we have actually covered this article 2.3 as free vibrations of an undamped torsional system. So what I recommend the students that the current lab session is not a new lab session, but students will be actually treating it as a part B for the previous lab session for article 2.3 free vibration. So students will be writing it as the part A, for example, and the current lab session that I am now going to give the instructions as the part B. So this is part A, and now part B will be guided. So we are familiar the background theory that I have showed in the previous lecture as well, and again I can show here the necessary equations and along with their numbers here. This was actually the schematic diagram. This was the schematic diagram, and these were the equations of motion for the undamped torsion system. This was actually the natural frequency. Kt was torsional constant stiffness, or torsional stiffness you can say, and J naught was actually the polar mass moment of inertia for the rigid disk, and this was actually the natural time period, and this was actually the linear natural frequency f subscript n, and here this was the formula for calculation of polar mass moment of inertia alternatively. So we had covered, and this was actually the model that we had created, and you remember that three methods or ways were used for creation of geometry. First was that, for example, the shaft was created as the line body, and this rigid disc was also created as the line body with the circular cross section of different sizes. And secondly, this rigid disc was used as the extruded model or solid body, and this shaft was used as the line body. And then again both were used as the solid bodies, means rigid disc was also extruded as the solid body, and this shaft also extruded as the solid body. Was created as the solid body. So this third technique was used as the final understanding for the model. So the other necessary data that was used here for the creation of geometry, you can consult the previous lab session dated perhaps 1st of April 2026, if you remember. The data for the this shaft was used as 0.05 as the radius and 0.1 as the diameter, and its length was assumed to be 1 meter. And for this rigid disc, the data was used 0.5 as the radius. So diameter for this rigid disc was used as 1 meter, and its thickness, here you can see its properties. For example, this is the rigid disc. See its properties here, that its mass was used as 1 kilogram, such that this volume was actually mass per unit volume, means this mass was used upon this volume, mass per unit volume, and its density was achieved as here listed. The steel disc, its density had 12.733, and observe here that its bounding box means here, if the dimension you carefully note, length is length x 1 meter, that means in the x direction, means for example in this direction, means this diameter is 1 meter also, and its length y means in the y direction. So this thickness in the y direction, this was used as 0.1 meter, and length z means in this direction or in this direction diametrically, that was also. So its diameter for this rigid disc was used as 1 meter, and its thickness, that was extruded as to be 0.1 meter. And for the shaft, if you see, so here you can observe that its length along x, as you can say here, in the x direction means 0.1 meter, that means is diameter, sorry, this diameter in this direction was 0.1 meter, so radius was 0.05, so in the z direction as well, and length in the y direction, so this was used as y. And so two material were created, and furthermore here fixed joint was were used. So this fixed joint was actually suppressed later, because this was created for the different geometry, means for line bodies for example. So the final geometry was shown here as the fixed joint solid to solid, means both were the extruded model as listed here. So I am just summarizing what was done in the previous lab session. In the analysis setting, mode was set to be 1, and in the remote displacement, that was very important, that this face was selected for the rigid disc. So this face can also can be selected, or you can select this circular face as well, or the other face which is in the background, means in the on the bottom of this disc. So there are actually total 3 faces, this circular face and the circular face, this upper face that is connected with the shaft, and its other face which is parallel to this face. So there are total 3 faces, so any face can be selected as the, and remember that rotation y means all linear parameter to be 0, rotation along x or any axis which is located in the plane of the face, that must be 0, that must be 0. So if you select this face, you can select its bottom face which is parallel to this face. So in any case the rotation y is free. Why rotation y is free? Because y is actually the polar axis which is perpendicular to this face. So and here we had applied the fixed joint with this face of the extruded shaft and this face. So we had actually obtained the frequency as to be 391.06. Again in the formula I can make you explain. You must remember that this KT is actually for the solid shaft, remember, because that is actually elastic, because this capital G is the shear modulus. But J naught, as you can observe here, this is for the rigid disc. This J naught is for the rigid disc. So you must clarify this difference in your minds. Now for the current article, the article is 2.6.5 torsional system with viscous damping. We had actually learned these equations in the theory lecture, and we are familiar about their derivations. This was actually the damped frequency, this was the natural frequency. You can just observe it here, and this was the schematic diagram here. And here you can again observe that the KT is for the shaft, here you can observe. But as you can observe that CT means torsional damping constant is for this rigid disc, because mainly this rigid disc will be actually rotating or oscillating in this fluid. So this is a fluid of viscosity as shown here, which is torsional damping constant is C subscript D. So here this damping factor means the ratio of the torsional damping constant to the critical torsional damping constant. So it's like its linear equivalents. So this was actually, because in the linear system that was actually 2 m omega n. So for the torsional system, m has been replaced with j naught, so 2 j naught omega n. And again its other alternative was in the linear case 2 square root km. So here k is replaced by kt and m has been replaced by j naught. So for the current analysis, damping factor, as I had suggested, that you will be assuming it to be between 0 to 0.3 or maximum 0.4, not above this, if you want appreciable cycles or frequency for the damped vibratory system. So now actually I have attempted this model and I am just demonstrating, or briefly, I am not giving you the instructions in detail, that I am not applying all the constraint or all the joints freshly. I am just making you see what I have done. So in the editing mode, and here you can observe that what I have done, what you will be doing, that you will be creating a parallel model module along with this A module. You will be actually launching a parallel model module, and you will be actually interlinking this engineering data and this geometry with each other. And furthermore, this you will be clicking on this model cell B4, and after that what you will be doing, you can observe it here what I have done, that this previous joint that was actually for the undamped system that has been suppressed, means the joint, fixed joint, means the fixed joint between this face, between this face and the lower face of this shaft, there was actually used a fixed joint, so you will be suppressing it. So important point here is that how damping effect will be added up, because previously we had demonstrated the undamped system, but for the current case this was very important, that how the damping effect will be introduced. So what I have got the information from my experience and going through internet and different research websites. So I have learned to make you understand that you will be actually creating a revolute joint. So you will be clicking on the connections as previously you have been doing. So click on insert and click on joint here, and in the joint you will be creating here, for example I can show you just that you will click on joint, and here for example this is the joint, so you will be selecting revolute from here. So you will be selecting revolute from here, and once the revolute has been selected, for example I can make you observe here that select revolute joint, and here you will be observing that as soon as you select the revolute joint, you will be obtaining two informations here that will be required. One is the torsional stiffness. So torsional stiffness, that you can observe it here, that KT, this is the torsional stiffness. K subscript T is the torsional stiffness, and the other information that it requires, that is torsional damping. So torsional damping is actually C subscript T, means torsional damping constant. So very important thing is that here, that you must observe it here, its units, because you will be making a mistake here. The units in that you will be inputting here, that is in torsional stiffness is Newton meter per degree. Remember, by default. So in the torsional damping constant here it says Newton meter second per degree. So very important thing is that here by default the units for torsional damping constant are Newton meter second per radian in this formula. So from this formula you will actually be getting the value or the magnitude of the torsional damping constant with the units of Newton meter second per radian, not in degrees. So for degrees you will be multiplying the value of torsional damping constant in radians to multiply it with pi by 180, because per this will be in per radian, so you will be multiplying it pi by 180, means pi radians by 180 degrees. So radian with radian will be cancelled out, and you will be obtaining the torsional damping constant per degree. So that is very very important in this respect. In a similar manner, again kt, here you can observe here that this kt is default unit from this formula is Newton meter per radian, but in the formula in here you observe that it is Newton meter per degree. So what you will have to do, that you will be actually multiplying it with pi by 180. So radian will be cancelled out with radian, so you will be obtaining Newton meter per degree. So this is very important thing. Actually I have not shown you here the calculations, so that was actually quite simple thing, so I have told you orally, so you can do it yourself, so that you have a good learning point for this. So remember this is very important thing, that whenever you will be given a problem, you must remember that here you must input Newton meter per degrees, and here Newton meter per second per degree, not in radian. By default these formulas will give you values in radian, so you will be actually converting them into degrees, otherwise you will be obtaining false results. You cannot you can observe it, you cannot change here into radians. So might be in the options there might be available some way to change this into radian, so but you don't go for that way, so use as it is as shown here. So simply you can convert your values as required. So after that, the very important thing that you will be doing, as I have inserted here the joint, this joint sorry, in the this B module here. So what you will be doing, that after inputting these values, so what are these values, what I have used here, torsional stiffness. So torsional stiffness, as you are already familiar, previously we had actually didn't use this, because we had used here the fixed joint. We had used here a fixed joint, as you can observe it in the A model, that here it was used a fixed joint simply. So actually the value for torsional stiffness was not used, but for this case this is very very important thing, that you will be inputting the torsional stiffness value as calculated. So what is that value, and you remember that that will be calculated with this formula. So here you will be, this is pi and capital G. So remember that in the engineering data, remember this engineering data, you will be derived from, in the derived from column you will be selecting here shear modulus and Poisson's ratio, this, and here you will be observing this will be available. The value you can use the default value 7.6923 10 raised power 10. So this is the value for capital G. So you will be using the value for the torsional shear modulus as 7.6923 10 raised power 10, and after that d has the value of 0.1 and raised power 4 and divided by 32, and length is 1. So this will giving you the answer as to be 755 189.785. So the value for kT that you can verify is 755,189.785 Newton meter per radian. So when you will be multiplying it by pi by 180 degrees, you will be obtaining the value of the torsional stiffness to be 13180.548. 13180.548. So this will be the value for torsional stiffness in Newton meter per degrees. So that you will be using the value here, as I can show you here, because I had used this revolute. So I have used here 131 80.48. So actually here you can observe the actual value, because the system actually rounds it off here when we finish it. So here this is showing you the actual value 13180.548. So this is the value for the torsion stiffness in degrees, Newton meter per degrees. So after that, that is the torsional damping constant. So torsional damping constant is calculated from here. Here you can assume the damping factor, torsional damping factor you can say, as to be 0.3, and the critical damping constant, as you have now calculated kT already, that was actually 131.8.548. But remember again that here that you will be using the original value of kT in radians, means you will be using here the value 755,189.785. remember, not in degrees. Here the value for kT in this formula will be used in radians, not in degrees. So in the value in the radian, 755,189.785 Newton meter per radian. And J naught you can you know that the value for J naught is half mr square. So m is the mass of the rigid disc. So that the mass for the rigid disc, as you know, that is 1 kilogram. You are familiar that the mass for the rigid disc is 1 kilogram, and R is actually 0.5. R is 0.5. So this comes out to be 0.125. You can calculate it here, or you can approximate, show its value here, 0.12412. So this is the actually ANSYS calculated value, but it's actually true realistic value that you can calculate is 0.125 for this rigid disc, having its radius to be 0.5 and mass of 1 kilogram. So using the formula half mr square, which is actually the formula for calculation of polar mass moment of inertia. So the value, so when you will be multiplying the value of kT by J naught, so you will be observing that yes, you will be uh, you will be uh, obtaining the value as when you will be multiplying it kt with j naught means 755,189.785 multiplied by 0.125 and taking its square root and multiplying it by 2 you will be obtaining 614.487. So after that you will be multiplying it with this damping factor which has been assumed to be 0.3, so you will be obtaining 184.346 Newton meter second per radian, Newton meter per second. So the value for the torsional damping constant, mean actual torsional damping constant using this formula is 184.346 Newton meter second per radian, So when you will be multiplying it with pi by 180 to convert it into degrees, so you will be obtaining 3.2174 Newton meter second per degree. So that value that you will be using it here, here you can observe, I can show you here in this revolute joint here that this is the value 3.2174 Newton meter second per degree. So this value will be used. So the next point that will be which face has to be selected. So in this revolute joint you can observe here, just I am using this revolute just to make you observe. I have shown you the applied joint here and with all data, so I am just making you understand from this joint 3 that you will be here, you will be selecting, you will be clicking on this remember I have used here body dash ground for this rigid disc, because this rigid disc will actually be oscillating with respect to the ground, body dash ground for this rigid disc. So you will be clicking on at least you will be selecting this circular face, but as you can observe it here, this is up to you. You will not be obtaining different results, that you can select this face and the bottom face, means total 3 faces. So for the multiple face selection you will be clicking on, for example, this face, and then you will be pressing control button and this face, and here you can just rotate it like this, and after that you will be clicking on mode and single select, and then press control button again and then select this face like this, and here you can observe I have used here it shows here 3 faces. So you can completely envelop this rigid disc, because this whole rigid disc is actually dipped in the viscous fluid, So you can either select this face or upper face or this circular face, at least one face, but as a precaution you can select all 3 faces, so that will not actually be making any difference in the result. So here like this. So again I am now deleting this joint, because I had actually used only this joint to make you understand only, just for demonstration purpose. So now I am deleting so that it does not affect my analysis. So in this way that joint will be become available, and that green tick mark will be done, and like this. So the important thing is here that you will actually in making this previous fixed joint as to be suppressed, means that joint must be suppressed or deleted. That joint, as you can observe it here, I have clicked on it here, and here as you can observe it here, it is mentioned unsuppressed, but when it will be unsuppressed, then that means that joint will be available. So here suppress will be mentioned here, so you will be clicking on it here. So this cross will be put here, and in this way that the original fixed joint will be suppressed, means that will not be available and will not be making any effect on our analysis, and only this joint 2, and this joint to revolute joint has been applied on this rigid disc, remember, not on this shaft, because this actually rigid disc will be actually oscillating in the viscous fluid. This shaft is actually elastic, this has no role, means actually the viscous fluid will be acting on this rigid disc, on this mass of moment of inertia J0. So this is the important thing. And after that, what we will do in the analysis setting, the very important thing is that you will be clicking on this solver control, and here it will be written damped, and by default here will be listed no, by default, so you will be putting it to yes. And in the rotodynamic control, you can also make this what is written here, I am not it is clearly I am not seeing it. This is Coriolis effect, so you will be setting it to on, or it doesn't affect our analysis, you can leave it, or as a precaution you can set it on. And after that, the remote displacement has the same settings as you have previously done. You can either select this face or its bottom face or any three faces like this, and this polar axis to be as free. And after that, what you will be doing, that you will be this fixed support is as previously, so that is not making any difference. And these are the necessary settings. Other data is quite same. This disc, this shaft is actually massless, as you can observe it here. Here you can observe it here. This is the structural steel shaft, so it is actually somewhat massless because its density is very less, and only this point mass is actually, or this mass for this rigid disc is actually affecting, and this rigid disc has actually this is the structural steel disc. So a respective material have been used, and after that what you will be doing, the final you will be clicking on the solution and clicking on solve, and you will be obtaining the results. So here in the total deformation, you can observe it here, the damped frequency is 373.17, and the modal damping ratio that has been verified, you can observe it here, 0.299, so that has also been verified. So now I will orally be speaking some calculations that you can verify it yourself, that the damped frequency that you can observe it here, this damped frequency. So when you will be multiplying it with the natural frequency, and the natural frequency, as you had observed, that was actually k naught by kt by j naught, and the value for kt that you had used 755,189.785 and divided by j naught, which was calculated as to be 0.125. So when taking its square root, the value that we had achieved, that was 2475, 2475.95, 2475.95. And when we had actually divided it by 2 pi to obtain the linear natural frequency, means small f subscript n, so the value that we had obtained here was 391.19 theoretically. And here you have also observed in the undamped torsional system, the value that you had obtained 391.06. so this was actually the undamped natural frequency. And in the B, this is 373.17. this is the ANSYS model damped frequency. So for the damped frequency, so you had actually used this formula WD, so 1 minus 0.3 square. So here when we had multiplied it with the omega n, so omega d that I had obtained was actually 2361.9, 2361.9. omega n was 2475.95 and omega d is actually 2361.9. and when we had divided it by 2 pi to obtain the damped linear frequency, so the result that I got was 375.9, 375.9. and here you can observe the answer is that ANSYS model gave 373.17. so that means the theoretical result that I have calculated have closely, very closely matched the ANSYS model results. So in this way, this analysis has been completed, and you can write it as the part B for the previous lab session for the undamped torsional system. So thank you all. If you have any question, you can fairly ask, and you will be similarly creating a fresh model, or you can simply interlink it like I have done here. And if you have any problem, you can fairly ask. God bless you all. Thank you. Assalamu alaikum.